dear friends. So what you see on the screen is very simple question about second law of about your comprehension of the second law of thermodynamics. This is just to check whether you already understood the second law of thermodynamics, and that response would help me initiate the discussion on the new topic which I would be beginning, namely exergy. Okay. The prerequisite of this lecture is that you must have seen the videos which have been shared with you by Professor Murukar. Okay. And you must have been revising the concepts which are already taught to you. So these are the prerequisites for this discussion on the new topic, namely exergy. Okay. So a very simple and a straightforward question has been asked, and obviously the responses are encouraging. Okay. I find that most of the students, or majority of the students, have answered it incorrectly, right? And that is very surprising, because that shows very poorly on us basically, because if you are not comprehending, then it is our failure, or it could be that it is your failure because you are not studying at home. So whatever, but as I see from the responses which have been recorded by GoToWebinar, about of the students who have voted, about 50% of the students have answered it correctly. Okay, and the remaining 50%, in fact, more than 50% of the students have given a wrong answer to this question. Okay, so I need to, before I go to the concept of exergy, I need to discuss this a bit in more detail. So let me close the poll and show you the results. About 85% of the students voted this answer, and let me show you the result now. Okay, so I'm closing the poll and I will be showing you the result. Okay, so the poll is closed now, and I'm sharing the results with you. So you see the results here. The question was, according to the second law, all heat can be converted to work in a heat engine. Whether this statement is correct or whether it is wrong according to the second law of thermodynamics. So those who have been attentive to the lectures and those who have been viewing the videos which have been shared to you, that percent of the students, means around 47% of the students who have voted, they have got the right answer. Okay, so 47% of the students who have written the answer as false, okay, they are on the right track. Okay, they have understood the second law statement, especially the Kelvin Planck statement of second law of thermodynamics. So the correct answer to this question is, according to the second law of thermodynamics, all heat cannot be converted to work. Okay, all the heat cannot be converted to work. That is the correct statement. Okay, so the statement that all heat can be converted to work in a heat engine is wrong. It is a false statement, and this 47% of the students are intelligent enough to understand that this is a false statement. Others, the 53% remaining, they need to take extra efforts in listening to the videos, okay, and remaining attentive, also doing some self-study. So before I begin with the next topic of exergy, let me ask you another question. I'm hiding this poll now. Poll result I'm hiding, and I would be running the second question, which is again related to the same concept. Okay, which these concepts are extremely important for understanding the topic of exergy and available energy. Okay, so let me launch this poll now, and you see the poll question in front of you. This is about a Carnot engine. Okay, so let us see now how many students have really understood this question, the concept, I mean. Only 8% of the students have voted, and about 40% are yet to vote. So this again is a very important concept. If you do not follow this concept, then it would be difficult for you to understand the concept of exergy and available energy. Okay. Yeah, Vedant, you're right. So let me close the poll and share with you the results. The question is about the second law of thermodynamics, and as I am repeatedly telling you that why am I emphasizing this second law of thermodynamics? It is because if you want to understand the concept of exergy, then you need to be very clear on the second law of thermodynamics statements. Okay, you must have internalized what exactly the second law is trying to tell us. Okay, you must have understood what is a Carnot engine, right? Without these concepts, it won't be possible for you to comprehend the concept of exergy. So please note that that is the reason why I'm repeating these poll questions, which have been asked many a times during our earlier discussions on second law. So this is a sort of repetitive polls, but still I find that many students are not comfortable with these concepts. Okay. So I'm closing the poll now because we have already run out of time. Only 75% of the students have voted, and of them, about 65% of the students have answered the question correctly. Okay, so I would be closing the poll and I would be showing you the poll result. Okay, so I'm closing the poll. The poll is closed, and here is the result. So the result which you see over here. So according to the second law, Carnot engine has 100% efficiency. So 35% of the students feel that Carnot engine has 100% efficiency, which is totally wrong. Okay, no engine Not even a Carnot engine has 100% efficiency. Okay, please note that. And hence the answer is false. And 65% of the students, that 65% is also a misleading figure because only 77% of the students have voted. So of the 77% students who have voted, of them the 65% have answered it correctly. The correct answer is false. Okay, and then I'm hiding this poll now, and I would be uh, taking a last poll question, which would then uh, give us the necessary introduction for the concept of exergy. Okay, so this is again a question related to the second law. The question is in front of you, so you can now answer the poll. Actually, there is a one mistake in framing the question. The question is, which engine can give us maximum work from the given heat input? Okay, which engine can give us maximum work from the given heat input? From the given heat input, there are three options. One option is that no engine can give us maximum work. Second option is that converting heat to maximum work is not possible. And third option is that a Carnot engine can give us the maximum work from a given heat input. Okay, so 50% of the students have voted this. I would be giving you another 1 minute for voting this. Okay. So I'm closing the poll question now, and we'll begin the discussion on the concept, a very interesting concept called as exergy or available energy. And I answered it. So let me close the poll and show you the result. Okay. So the whiteboard is in front of you, and I have started the discussion on the new topic, exergy. Okay, exergy, or what is also called as available energy. Okay, so the plan is to discuss the relevance of why this specific term exergy or available energy is defined in thermodynamics. What is the advantage of defining this term exergy when we already have a number of terms like energy, entropy, and so on? So why do we study a new term called as exergy? That I'm going to discuss. Okay, that is the relevance of the term of exergy. That is the idea which which I have in mind while starting the lecture today. This exergy, if you want to understand exergy, and as we had discussed in the poll question, we need to understand the second law of thermodynamics and how the second law of thermodynamics is different from the first law of thermodynamics. So you all know that first law of thermodynamics, first law of thermodynamics, it is the law which helps you to analyze the system on the energy basis. Okay, any system which you take, a practical system like uh, internal combustion engine, IC engine, okay, or you take a thermal power plant, coal-based thermal power plant, okay, thermal power plant, or you can take a gas turbine power plant, okay. So any conversion, or you can take devices like heat pump and refrigerator, all this, okay. So these systems you see, heat pump, refrigerator, what you find is that these systems are basically systems involving heat to work conversion or work to heat conversion. Okay, such sort of systems. Okay, and what the first law helps us is the first law will help us to. Okay, I guess that the whiteboard is not seen. I need to share the whiteboard. Let me first uh, show you the whiteboard. Okay, this is the result which you are seeing from the earlier question. The earlier question, the result is Carnot engine is the correct answer, and 83% of the students have answered it correctly. So now I'm hiding it, and hopefully now, no, you are not yet able to see the whiteboard. So let me try changing the presenter. Okay, I'm trying to change the presenter. Okay, let me change the presenter. Let me just take somebody from you, make you a presenter, and then I will be making Kunal as a presenter. Kunal, I will try to make a presenter. Okay, and then I would change it back to. Okay, let me change the presenter. Okay, Kunal is now a presenter, but I would be. Okay, right. So what you see is now the whiteboard, and I have written the term exergy and available energy. Exergy, available energy, availability are used to denote the same thing. So what we are trying to figure out is why this exergy term is important for us. Okay. So first thing is you need to understand that exergy or available energy insights can be obtained only from the second law of thermodynamics. What the first law of thermodynamics helps us to understand is that there is an energy balance. There is an energy balance. So we have seen that when we had applied the first law of thermodynamics to a closed system, we talked about Q is equal to delta E plus W. When we talked about applying the first law of thermodynamics to open systems, steady flow systems, we had written the steady flow equation. So all these equations help us to relate the input and output. However, the first law of thermodynamics does not differentiate between the different forms of energy. Okay, that is, we can say that it is a limitation of the first law of thermodynamics. I mean to say that if we talk about, let us say, two forms of energy, one is the heat and other is the work. Okay, so if you are talking about, if you are comparing heat and work from the first law of thermodynamics, then the first law of thermodynamics would simply give us an energy balance. For example, let me just show you one engine. Okay, one engine. Okay, so let us say that there is an engine here. There is an engine. Okay, so this engine, if you want to apply the first law of thermodynamics, so you know that engine means there is some heat being supplied, there is a work being produced, there is some heat is rejected. Okay, and if you, let us say, if you take a source from which the heat is being supplied, and then there is some sink where heat is rejected. Okay, so what is, when you are saying that we are figuring out what is this? So from the first law of thermodynamics, what we could say is that heat supplied is equal to QR plus W. Okay, so this is the first law applied to a heat engine. First law applied to a heat engine, right? Now, this first law does not differentiate between, let us use a different pen. The first law does not differentiate between this heat and work. Okay, so if you ask the first law of thermodynamics, suppose you are asking the first law of thermodynamics whether, suppose this is 100 kilojoules of heat is supplied. So whether one can obtain, if you are supplying, let us say, 100 kilojoules of heat to a heat engine, right? So whether one can convert this 100 kilojoules to 100 kilojoules of work, 100 kilojoules of work, whether this conversion is possible or not, that if you ask the first law of thermodynamics, then the first law of thermodynamics would not be in a position to tell you anything about it. Okay, so the first law of thermodynamics would say that, okay, I am not in a position to comment on that. Okay, I won't be in a position to provide you any information whether one can convert 100 kilojoules of heat to 100 kilojoules of work. That is, whether one can convert the entire amount of heat to entire amount of work. That the first law of thermodynamics is not able to answer. Okay. Now, if you ask the second law of thermodynamics, whether second law of thermodynamics, the Kelvin-Planck statement, that whether one can convert 100 kilojoules of heat, 100 kilojoules of heat to 100 kilojoules of work, whether this conversion is possible or not. The second law would immediately tell us that such a conversion is impossible. Such a conversion is impossible. Now, mind well that this Q is energy, right? W is also a form of energy, right? W is also a form of energy. So what the second law is telling us now is there is some form, this energy which is in the form of heat, this energy which is in the form of heat cannot be converted to work entirely. Cannot be converted to work entirely. Now this gives us, if you think deeper, that why that's so? Why is that you cannot convert the 100 kilojoules of heat, okay, through some mechanism, through some engine, to 100 kilojoules of work, okay? So the reason why you are not able to do that is, the reason must have to do with the quality of energy. The quality of energy. It means that though this is 100 kilojoules, though this is 100 kilojoules of heat, and though this is 100 kilojoules of work, the meaning is this 100 kilojoules of heat isn't the same as the 100 kilojoules of work. Okay. From the second law, we can now say that heat is a different quality of energy and work is a different quality of energy. What we can say now is, though, let us say in our example, both having the same quantities, that is, we have 100 kilojoules of heat and we have 100 kilojoules of work. However, 100 kilojoules of heat cannot be converted to 100 kilojoules of work, meaning that the energy in the form of heat is of a different quality and energy which is in the form of work is of a different quality. If you talk about, though the second law does not say, but in practice, if you talk about a conversion of 100 kilojoules of work, to, let us say, 100 kilojoules of heat, 100 kilojoules of heat, then this is possible. There is no second law limitation for converting the 100 kilojoules of work to 100 kilojoules of heat. It means that you look at this. So if you are having 100 kilojoules of work, 100 kilojoules of work, you are not able, you are able to convert it into 100 kilojoules of heat, right? You are having 100 kilojoules of work, you are able to convert that 100 kilojoules of work to 100 kilojoules of heat. However, if we are having 100 kilojoules of heat, we cannot convert that 100 kilojoules of heat to 100 kilojoules of work according to second law, meaning that this work must be of a higher quality energy. Okay, what the meaning is? The meaning from this is, from these two examples, if you take that, if you are having 100 kilojoules of, it is possible for us, okay, theoretically, to convert this 100 kilojoules of heat to 100 kilojoules of work to 100 kilojoules of heat. This is possible theoretically. Possible theoretically means the second law does not limit this conversion. But if you think of 100 kilojoules of heat, and if you think of it that theoretically, can we convert that 100 kilojoules of heat to 100 kilojoules of work, then even theoretically this is not possible. Even theoretically this is impossible. Meaning that if you look at these two things, then what it means is that this heat has to be of a lower grade. Heat has to be of a lower grade, and this work has to be of a higher grade. So work is a high grade energy. Okay, we can conclude that work is a high grade energy and heat is a low grade energy. So we can convert the high grade energy. We can convert the high grade energy to a lower grade energy, but we cannot upgrade. We cannot upgrade the energy. We cannot upgrade the lower grade energy to a higher grade work. We cannot upgrade the lower grade heat to a higher grade work entirely. Okay. So in a way, if you look at this discussion, in a way, the second law of thermodynamics brings in the quality aspect of energy. Are you getting the point? In a way, the second law of thermodynamics brings in the quality aspect of energy. Okay. I hope this is clear to you. Is this clear to you that what does the second law give us? What information the second law gives us? What does the second law gives us? What information the second law provides us? What does the second law talk about energy? The second law does not talk about the quantity of energy. The second law, yeah, that is correct, Gargi. The second law brings in the quality aspect to energy. Second law brings in the quality aspect of energy, right? Tanaya, you are right that we are talking about now the quality of energy. So as Tanaya is saying, the importance of quality of energy is to be understood, and the first law of thermodynamics is not able to differentiate between different forms of energy. So we need and the energy per se, the term energy per se is not able to differentiate between different forms of energy. We need another term to differentiate between the qualities of energy, and that term is called as available energy or exergy. That term which talks about the quality of energy is called as available energy or exergy. I hope that is clear to you. Okay, that this exergy or available energy in a way talks about the quality of energy. Okay, is this clear up to this point that this exergy or available energy is basically talking about the quality of energy? Yeah, thank you, Gargi. Anybody else who would like to say something that you have understood, whether the second law talks about the quality of energy and the term, we need a separate term called as available energy to talk about quality? Okay, all right. So let me now proceed to our discussion on the exergy or available energy. I have not yet defined about exergy, what is exergy or what is available energy. I have simply given you the context, okay, that how this second law of thermodynamics, the quality assessment, is able to convert only partially the heat to work. It means that this heat is a lower grade energy and work is a higher grade energy. Okay. If you had listened to the video of Professor Murukar, another example was given, okay, to help you understand the quality aspect. Okay, so let me again take the same example which has been referred to in the video. Okay, so let us take some practical example, like you know that you know what is an electric heater. You know what is an electric heater. Okay, and you know what is engine. Okay, your petrol engine, for example, petrol engine or diesel engine, petrol engine or diesel engine. Okay, now if you ask me, okay, if you ask me that, Ganesh, what you are saying, exergy is supplied energy. Ganesh, no, exergy is not supplied energy. Let me tell you what is exergy later. Okay, Ganesh, we'll discuss that, Ganesh, don't worry. Now let's try to concentrate your attention on what the example which I am giving you. Okay, uh, okay, so let us take an example of electric heater. Now what does the electric heater do? Electric heater, tell me the conversion from which energy to which energy, which energy to which energy. Electric heater conversion is from which energy to which energy? Yeah, anybody else? Anybody else? It converts the electricity, that is electrical energy, to heat. To heat. Okay. Now, if you look at, yeah, Ganesh, correct. It is correct, Ganesh. So, electric heater would convert the electricity to heat. Okay. Yeah, Munish, Tanya, sorry, Tanya, that is right. It is converting the electricity to heat. Okay, And what about the petrol engine? What about the petrol engine? What about the petrol engine? Kamlesh, what about the petrol engine? Kamlesh Sonon is saying it is chemical to work. That is correct. Okay. Uh, if you talk about combustion in petrol engine, okay, there is a combustion in petrol engine. So we would that is correct, chemical to work. But I would go to a slightly different grade. I would be restricting my discussion to heat to work conversion. So the chemical energy is ultimately converted to heat energy, and heat energy is converted to work. Okay, Kamlesh, right? So in a way, chemical energy is converted to heat and heat to work. Okay. So as Kamlesh is saying, heat to work. Okay, heat to work. So uh, in my model, I am just simplifying the thing. I know that it is basically the chemical energy in the petrol or diesel, but when you are having a combustion, you know that combustion is an exothermic reaction, and ultimately what you get is heat. And this, so we can say, in a way, we can say that heat is getting converted to work. Heat is getting converted to work. Now, if you ask, if you ask what theoretical efficiency of the electrical heater and what is the theoretical efficiency of the diesel engine and the maximum efficiency, can you tell? Can you give some number? Can you give some number that what is the as the question is what is the typical efficiency of a what is the theoretical efficiency? Do you have some number? Or let me simplify the question. Can we theoretically convert? Can we theoretically convert the entire amount of electricity which we are supplying to heat? Okay, to heat the water. And the second question is, can we convert the entire amount of energy which is released by the combustion of the fuel in the petrol engine to shaft work? To shaft work. Okay, there are two questions. One is, can we convert the entire amount of electricity into work? Into heat in the electric heater. Can we convert the entire amount of electricity into heat in the electric heater? This is the first part of the question. Tejas is saying no. Theoretically, I am talking about theoretically. Okay, theoretically. Himanshu is saying that no for both the questions. Tejas is saying no. Any answers? Anybody who is trying to? The answer is theoretically. Theoretically, we can convert the entire amount of electricity into heat. Okay, we can convert. It's yes for first. Yes for first. Yes, Tanaya, you are right. It is yes for first and no for second. Okay, it is yes for first and no for second. Right, Tanaya, you are right. So we can theoretically convert 100 the entire amount of electricity to heat 100%. This is possible theoretically. This is possible theoretically. Why theoretically? I mean that there is no restriction from the second law. But when I'm saying theoretically, there is no restriction from the laws of thermodynamics to convert electricity to heat. There is that in the market survey, if you do a market survey, the electric heaters would have the efficiency greater than 90%. Okay, very high efficiency. Electric heaters would have a very high efficiency, 90% and above, because we are talking about converting a high grade energy. We are talking about converting a high grade energy to a low grade energy, which is possible. Which is possible. Okay, we can convert the high grade energy to a low grade energy, which is possible. Or in other words, we say that because electricity is of a different grade, a higher grade, such a conversion is possible. But in the engine, you won't find the engine efficiency is greater than 40%. Okay, so this is the limit. Our 40%, 50% is the engine efficiency, best engine efficiency, right? So why is that so? That is because the heat is a low grade energy. Heat is a low grade energy, and you cannot convert the low grade energy to a high grade energy. So I hope that now you have figured out that though we are talking about energy as per the second energy is always conserved, destroyed according to the first law of thermodynamics. However, this statement is meaningless. Okay, because practically speaking, though the energy is not destroyed, however, the useful form of energy is the systems. You'll find that any energy conversion phenomena in any energy conversion devices, okay, you'll find that energy is always conserved. There is no question of energy being destroyed, because that is what the first law says. Energy is always conserved. So actually the term which we always use sometimes conservation, because energy is always conserved. However, you need to understand that, and what is being destroyed, that being destroyed is called as exergy. Okay, energy is conserved, but exergy is being destroyed. Okay, we are not yet defined exergy. Please note, we are simply looking at it from a conceptual angle. I have not yet defined what is available energy, what is exergy, that I have not defined. But I am now trying to bring to you, okay, the idea that though energy cannot be destroyed, however, the work potential of the energy is destroyed in energy conversion process. Okay, so the insights which we get from the first law of thermodynamics, that energy cannot be destroyed, these insights are no way useful in designing better machines. Because any machine you have from the which is being destroyed, energy is always conserved. We know from common sense, we know from practice, that something is being destroyed, but that something which is being destroyed cannot be called as energy. That is the reason we need to define, okay, a term called as exergy, which gives us in a way a better idea of what is being destroyed and what is to be conserved. Okay, so what is being destroyed is exergy is being destroyed. What is to be conserved is the work potential which is to be conserved. What is to be conserved is the exergy which is to be conserved. Okay, I hope that this gives you a sufficient background for starting with the discussion on what is exergy or what is available energy. I hope this introduction is clear to you. Is this clear? Whether whatever I had discussed is clear to you about the quality aspect of energy? Yes or no? Okay, Neha is saying it is destroy म्हणजे नक्की काय होते. Okay, Gargi will discuss what is that destruction means. What I will come to that. but I don't feel that we have sufficient time today for taking up that. In the tomorrow's lecture, I would discuss what is being destroyed. Okay, but whether this is clear to you that we are by defining available energy term than energy, and that term gives you different insights about the different insights which the term energy does not give us. Whether that is clear? May I saying yes? Anybody who would say yes? Kamlesh has understood, I guess. What we are finding the term called as energy for you. What I am trying to tell you, energy balance. Okay, we have written the energy balance equations. Both the energy balance closed system, which is Q is equal to delta one system, that is steady flow energy equation. Steady flow energy equation. So what are these equations? However, it is not the different converse. Would tell you that so work. They are having a very can be convert the high grade energy to low grade energy cent person, but you cannot convert the low grade energy to high grade energy cent person. Okay, this in a way tells you that there is something called as quality of energy, and this quality of energy we need to define. Okay, and the term exergy helps us to define that work potential or quality of energy. Okay, so I hope that this introduction helps you in appreciating the need for defining another term called as exergy. Okay, what is that exergy? How do we define that exergy? What is being destroyed, as Garge is asking? That I would discuss in tomorrow's lecture. So I'm ending this webinar. Have a good day, all of you. We will take up, we'll continue with our discussion on exergy. Don't worry, even if you have not understood this, we are going to spend considerable time in uh, seeing to it that you internalize the concept of exergy. It is very simple concept, okay, but it would take some time for you to digest this. Okay, thank you very much.